Let's continue then. So we are done with an introductory example, and let us now write our system. Is it recording? Yes. Let us write our system in more typical form that you can find in many books. Just change the notation a little bit and talk about the conditions that ensure existence and uniqueness of this solution. Paragraph 2. General formulation, uniqueness and existence of solution. So we can say that the system reads f of t, u of t, and u of t0 is equal to u0. So this is typically referred to as a Cauchy's problem for an ordinary differential equation. At this point, I'm not specifying whether this is a vector or scalar, but in our consideration of different various numerical methods, we will assume this is a scalar. As I said, it can easily be transformed to the vector case. So what we need to ensure, what conditions we need to ensure if we want the solution to exist and be unique. The following theorem is known from the theory of ordinary differential equations. So let the function f of t, u of t be defined at t from t0 to t capital, and for any u from minus infinity to plus infinity. You should say like this. And let this function, so all the conditions are on the right hand side. Let this function be a Lipschitz, if I'm not mistaken, he is written like this, Lipschitz continuous. По-русски это будет Липшиц непрерывно. Непрерывно по Липшицу. Знакомая тема?
Ну, я вот пытаюсь вспомнить, какие там...
Which means, that is. Что означает? That is, t of u1, Lipschitz continues at its second argument. An important note. At its second argument.
Just it has derivative from both ways?
It's like a lighter condition than the derivative existence. It's just it's the lightest possible, not the lightest possible, but very weak condition. So it says that the values of this function at two values of its argument does not differ more than the values of the arguments multiplied by some fixed constant. So there exists a constant L such that this inequality holds true. Then, in these conditions, equation or system has a unique, this especially for when this exclamation mark is used to say unique briefly. Unique has a unique solution. Not sure if in China you are using the same notation. Without a proof. So it's not a mathematics or differential equations course, so without a proof. And there is an important note that comes together with this theorem. So this theorem is one-sided. So this is a sufficient but not necessary condition. So which means that this system might have a unique solution even if this condition is not satisfied. But if this is satisfied, then we are asserting that it has a solution. And the node is two-sided. F is Lipschitz continuous. This is equivalent to the following. The derivative by its second argument at any t and u from its range does not exceed L. And it is constructive because it's easy to check. And a couple of examples. Example 1. Let's take f of t in this form, cosine of t plus u. Let's check. Would we have a unique solution in this case? What should we do to understand?
We should take a derivative.
We should take a derivative, right?
Yes.
F by u is equal to what?
Sine is t plus u.
Minus sine. Minus sine of t plus u. Okay, what can you say about the absolute value of this guy?
It's less than 1. Yes.
It's definitely less or equal to 1, which is L in this case. Hence, star has a unique solution. And another example. Let's take t of f of tu in this form. Check what form I want to take. Okay, t plus u to the power of 5. What do you say?
In general case, no.
Right? Correct?
Yes.
So, cannot say that this is bounded. No idea whether, как это пишется, может легко написать слово осел. Это еще не просто осел, если посмотреть словарь, смешной осел. По-моему, не так. Whether star has or does not.
Either.
Нет, это не either. Ли, это частица ли. Имеет ли решение. Does not have, has or does not have a solution. And this means that we have to use some other techniques or considerations to answer the question whether the system with this right-hand side will or will not have a solution. Just to indicate how it works. Okay, what's next? And now we are ready to talk about numerical solutions. By the way, did you want to discuss your practical work today? I don't remember. Did you?
I did the second one and I did the third.
You've done the second one and the first one.
Yes.
And did we discuss the second one?
No.
We didn't. So we have to reserve some time to discuss, right? Okay. Paragraph number 3. And we are starting the numerical methods. Paragraph number 3 will be called Euler's method. Okay. Paragraph 3. Euler's method. When we are speaking about numerical solution of any problem, approximately any problem, in most cases, the first thing we do is we introduce the mesh in the range where our free parameter is changing. In our case, the free parameter will be the variable t, and it changes from t0 to t capital. And the mesh is defined like a set of nodes, a set of nodes Tn. In this theory I'll be using index n, starting from t0, tn minus 1, tn, tn plus 1, and so on, to tn capital. Tn is equal to t0 plus n by tau, where tau is greater than 0 and n is equal to 0, 1, and so on. N. Am I right?
Mm-hmm.
Okay. The goal of the numerical solution is to build a table. I'm writing on the board to let people who are listening.
In this case, it's only the positive part without. Okay. Yeah. Sorry.
Do you don't like this condition?
Yeah, no, I like this condition, but I don't like the condition about the n. So it should be all sandwiches.
Integer numbers?
Integer numbers.
Why do you want them?
No.
T0 can be negative.
Mm-hmm.
Nothing prevents us to think that T0 is negative.
Okay.
I can allow T to be less than 0.
No, it doesn't matter because it's constant.
Let's say this. We can use all the methods to the negative direction of the t-axis. Doesn't matter. I guess. I hope I'm not mistaken. Now let's write like this. So the goal of the numerical solution is to build a table. What kind of table? Tn versus yn. What is y? We didn't see y yet. T0, T1, and so on. Tn minus 1, Tn. And here will come y0, y, and so on, yn. So instead of a continuous function u, instead of a continuous function u of t, we are looking for a set of values, and these values we will call y tau mesh function. And we need that these values that I marked with crosses here on the plot will be close in some sense to the unknown function that we want to find. So we are looking for the mesh function. Which is, I will write it, a set of nodes. So, geometrical considerations. If we take geometry, or consider geometry, from geometrical considerations, let's say this is to 0, t, and we know that there are infinite number of possible solutions, but thanks to the initial condition u0, we've chosen only one function, but we still don't know its shape at this point, at time t0. But what we do know at this point, t0, thanks to the equation that I don't have.
The angle?
Yes. We know the angle. Because this derivative du by t says that the tangent of the angle alpha. No, it's not horizontal, it should be horizontal. Alpha is equal to f of t0 u0. Tangent alpha is equal to f of t0 u0 that I know. We can calculate it. Since we know the angle, and since we don't have a red marker, we have a good one. Since we know the angle, we can construct a tangent line at this point to the unknown curve that we want to find. We can construct this tangent line. If so, we can go along this tangent line and move to the next point of our mesh, here. What we can do staying here? We can say that now we know an approximation y1 to the function we want to find. This is the value we want to find, and this is our approximation. Okay, so I know y1, and I also know t1. It is just calculated from the expression. So I can again estimate the tangent of alpha at point 1, which is f of t1 y1. And I can continue my destructive actions and find another tangent line. But this tangent line will not be a tangent line to the original curve, right? But to the shifted curve. New tangent line. I draw it. This is new angle. This is alpha 0, alpha 1. Okay. And I'm moving to the point t second. And I continue this procedure on and on. And so on. I will write another segment. Just one more segment. This is y2, this is y3, and so on. So as a result, we get this segmented line, which defines an approximate solution according to the explicit Euler's method. If we convert these geometrical considerations into algebra, we will find that every next approximation to the solution is defined through the previous approximation to the solution plus some correction. The correction is tau multiplied by Tn Yn. And this process starts with the knowledge of the initial condition. So this is the computational formula of the Euler's method. I'm sure many people have heard this even on mathematics. No need to have numerical methods course to hear this simplest idea. So this is the method that Euler formulated somewhere in 1.7. I don't remember for sure, but probably somewhere 7.5 or so. Together with the formulation of his ideas about the integration and so on. So, what else to say about this? There is another method of obtaining the same expression, and it has a very important use to obtain other more complicated methods. That's why I will explain it as well. Not only this geometrical approach, but also a more mathematical approach, so to say. Do we need the definition of the national? Okay, recall it. So this was sub-item number 1. This is sub-item number 2. Integration method. or better say integral equation method. Of obtaining Euler's computational formula. If we know, suppose we know an approximation at point Tn, Yn is known, then what we can do? We can integrate our original equation Tn plus 1. So we integrate, and this we know, we integrate our original equation over the next interval, going to the next point where we want to know our solution. Integral from Tn to Tn plus 1 of du by t dt equals integral from Tn to Tn plus 1 of f of t u of t dt. And on the left hand side we get un plus 1 minus un, right, is equal to this integral. So I said that we know the solution, the approximation to the solution at this point, and to derive the formula, a typical assumption is, let us assume that the exact, well, I'm not writing it carefully here, because I didn't say what un plus 1 or un means. Let us assume that u of t, the exact solution, is equal to our approximation for the time being. If this assumption holds true, then we can write a formula for the next approximation. We can write a formula for the next approximation. Next approximation, and at this point I can even write un plus 1, u of Tn plus 1, exact solution is yn plus integral but I don't know how to take this integral. Probably f is some complex nonlinear function. But I can approximately substitute, instead of this integral, its approximation using the methods that we discussed last time. One of the methods that we discussed last time, and let us, for example, use the left triangles method. If we use the left triangles method, we write the length of our interval is multiplied by the value of the function under the integral at the left part of this interval. And again, we are obtaining another approximation to this solution, which is exactly the expression I wrote before from geometrical considerations. What else to say at this point? So let's try to analyze the accuracy of this method. In order to analyze accuracy, the typical approach is to expand our exact solution, our unknown exact solution, in the vicinity of the point Tn. It's u of Tn plus what? Plus first derivative of it, right, by t, at point Tn, multiplied by tau, plus the second derivative divided by 2, right, at Tn, t squared, okay, plus, and so on. This guy is what?
Yes, but why we did the expansion by U from Cn?
I'm expanding the function, unknown function u, the exact solution,
Yes.
that I want to know at point Tn plus 1. I'm expanding it in the vicinity of the point Tn, where I supposedly know the solution by assumption.
So we just make it like this.
No, we took this assumption that on the previous step we did everything correctly, everything exactly. And then by assumption I know this term. This term I replace using the equation itself with its right hand side. And this term I will not touch at this point. What I will do, I will compare the exact solution at Tn plus 1 and the approximate solution at point n plus 1. This is gonna be the step error or local error. Let's compare. I'm sorry. At this point I should write a global error and then I will introduce local. Global means it is accumulated error from this beginning to this point n plus 1. U of t at n minus yn plus what? Plus f plus tau multiplied by f of Tn u of Tn minus this guy f of Tn yn and plus this expression for the approximate solution. We reached its end, nothing to add, right? Nothing to subtract actually. And here we have a remainder. Something that is changing together with the square of tau, okay? And with m2, if we use the same notation that we used before, this is the maximum value of the second derivative on this interval. Okay, m2, just some constant. If our whole solution is bounded, we can use this constant. It's bound for m2. What does this formula say? If this is 0, if our assumption works, then this guy defines, this whole guy defines the local error that we are doing by using this expression on one step. Step error.
Можно по-русски?
Конечно.
То есть мы делаем разложение Тейлора в функцию в
Точно.
точке у tn плюс 1 по функции в точке у tn.
Да. Мы предположили, что вот здесь вот в точке tn мы точное решение знаем,
Да.
так, и вот мы пытаемся представить точное решение вот здесь, как разложение в ряд Тейлора. Ну, просто математика.
Просто так.
Матанализ. А?
Просто мне, я не очень понимаю, почему так можно.
А почему не что, ну, любую функцию, и достаточно гладкую, которая имеет нужное количество производных, матанализ вспоминаем, любую функцию вы можете представить
в любой точке.
В любой точке дальше, там или ближе, влево, вправо,
Да.
если вы знаете ее значение в другой точке.
Да.
И ее производные.
Да.
Вот мы просто это сделали. Sorry, blank. So I've just explained why we can expand this function u that we don't know, but these are only theoretical considerations that we are taking here to estimate the error that we are doing. So the message that we have to or must read from this analysis is that this local error changes, well, this guy is zero by assumption, by our assumption, okay? So the local error is changing with this second power of tau. But I wrote letter E here, but I used this letter E to name the global error, I'm sorry. So I have to use another letter, epsilon is a local error and E is a global error, accumulated error. But this is only an estimation of the step error, local one. If we sum up such errors, I will not do this exactly or carefully now, but it is approximately equal. It is not exactly equal. It is approximately equal to I from 1 to n plus 1. Okay? And what it says, if this is tau squared by 2 by m2, we can move this term out of the summation because it doesn't depend on I. Okay? Tau squared by 2m2, and what we get in the sum? 1 plus 2 plus 3 plus 4.
Multiplied by n plus 1.
Multiplied by n plus 1. Why plus 1? I shouldn't have 1.
Maximum by n. No, this is correct.
I don't like n plus 1 here.
No.
I should have n here, probably.
No, this is correct because this is not depends on I. So we just
Okay, anyway, my message is that we can represent this as tau by tau, and tau multiplied by this n plus 1 is what? Is our length of our interval, right? So we have some constant c by the length of our interval by tau to the first power, and that's it, by tau to the first power. Well, my writing is awful. The message is this is the first power of tau that remains in the global error. So the global error has the order 1, unlike the local error for this method. Okay? Well, I hope those guys who will be watching this video will be able to understand what I'm writing here. Otherwise, ask questions. Okay. What's next? We've talked about the accuracy a little bit. Talked about accuracy. And one other thing that I want to introduce today is a modification of the Euler's method that we can obtain by simply changing the way that we use to approximate this integral. Let's try to approximate this integral on the right using a different method. So up to this point, you said you know the material, right?
Yes.
Maybe we will approach something new. Euler's methods. I should add to this Euler's method and its modifications. What's the number of the item? Do you remember? Item number what?
4.
4. So we had 3, right?
Mm.
Implicit Euler's method. So if we take again this integral equation that we obtained by integrating our original system, our original equation, we can use another method to approximate this integral, and the method that naturally comes to mind is, since we used left rectangles method before, let's use the right one, right rectangles. What we will get. Okay, earlier, for the previous method, we could start from y0, and we could recalculate the next solution and the next time step without any trouble, right? Because we just substituted the previous time step information to the right hand side, and we obtain the new approximation. Here, it's not possible any longer, because we have our unknown on the right, and even more, we have it under an arbitrary nonlinear function. It can be exponent, it can be cosine, it can be anything else, even non-classical functions, right? How to deal with this problem? How to solve it?
Convert it to yn?
No, we cannot easily convert it to yn. This was our decision. This is a problem which is known as a stationary point problem in numerical analysis, or just in mathematics. We can rewrite it like this: yn plus 1 minus yn minus tau f tn plus 1 yn plus 1, and that's it. So this is our function, equals 0. So phi capital from yn plus 1 is equal to 0. Stationary point problem. Why is it called stationary point?
Because it's always
Where? No. What is the point in this case? What we name the point? The point is this guy.
Yes.
This guy is considered to be from some space, probably probably it's a multi-dimensional space. If it is a vector, it can be a multi-dimensional space. If it is a vector, let's represent it with this point in space. And we are acting on this point with some operator, with some procedure, some algorithm. Do something with it. Recalculate it somehow. And this equation says that this operator phi capital cannot do anything with this point. It tries to move it somewhere. It tries to move it here or here, but it cannot. So our goal, in other words, our goal is to find such location in this space where our approximate solutions live. Find such point that operator phi capital cannot do anything with that. And there are a set of well-known methods to solve such problems. One of the methods is just this one. It says, let's start from some approximation to yn plus 1. Ideally, this approximation should not be far from the answer. And as such approximation, we can use, in our particular case, the previous solution on the previous time step. It's going to be a very good approximation to the solution on the next step. Right? If we start, and then we compute, I have to write 1 here, not I. And we can compute the next approximation to yn plus 1 by substituting our first approximation under this operator phi. If the operator phi satisfies some additional conditions, they are called compressive properties, so it must compress the space rather than expand it. Very mathematical terms, but nothing too complicated lies behind these terms. So this procedure is guaranteed to converge to the solution. So when we can continue on and on like this, recomputing new approximations from the previous ones. Okay, so this method is called the stationary point iterations. Stationary point iterations. А по-русски метод простой итерации. Метод простой итерации. So, what I'm saying is this strange approximate equation can be solved using some well-known mathematical technique or numerical mathematics technique. We can also apply Newton's method. Another well-known approach is Newton's метод Ньютона для решения нелинейных уравнений. Or, this is first approach, second approach, Newton's method. Okay. So, having said that, we understand that this problem is solvable. It's not something we cannot deal with. Okay? And in declarative mode, I will say that this method, its error, is also, global error, is also of the order of tau to the first power. If so, Why bother? Why should we spend so much effort to use this method and get only the first order of convergence? What's the positive property of this method that makes us use it at all? How do you think?
Why we use not this implicit, not explicit?
Yes. Why should we be using this implicit Euler's method instead of the explicit? Why we might be interested in it?
Because of the local error.
Local and global errors of both methods have the same order. This can be very, very easily proven using exactly the same procedure, but you will have to expand your solution around t. Let me think. Around another point. So, in the inverse of the considerations that we had before. So, what's the positive property?
Actually, explicit method also it moves faster than implicit.
Faster? In which sense? No, it's not faster because
we need to do this iteration.
yeah. Okay. Yes, you are right. Explicit method is faster because we don't need to do these iterations.
Yes.
Less effort, same order. Why bother? But I'm saying that there are problems for which this method is much, much better because of its stability properties. We didn't talk about stability at all yet, but its stability properties are much better than the stability properties of this explicit Euler method.
Stability, if it has some big drops.
If you have some small error in your initial data, for example, initial U0, so, let's assume that this U0 is defined with some error. And it is always defined with some error just because we are solving these problems on the computer. Rounding errors are always present. You can do nothing with them. Even if we don't think about physics problems from like experiment interpretation or errors associated with experiments. So this is always present, and stability discussion is about how this error is translated in time, further in time, whether it moves our curve very far from the actual solution, or we can control this error so it doesn't grow. And I'm saying without any proof, just qualitatively, that this implicit method is much better than explicit, exactly in this sense. It is much more stable.
It makes sense because I think it's obvious because we take the new point without the previous.
Well, you have a good sense of mathematics then. It's so obvious. Well, it might be obvious for simple problems, but the range of possible problems is so wide that it's not easy to say upfront for the general case, because your problem at hand might behave like this. Problem itself, without talking about numerics. The solutions might diverge in time. The exact solutions might diverge in time. If this is U0 and this is U0 plus delta U0, so the properties of the system itself might be such that the solutions diverge, or the properties of your system might be such that the solutions converge. These are two very different situations. This is more typical for like explosion problems, or what else? Maybe calculation of the planet trajectories in space. These problems tend to lead to the solutions that diverge very quickly if you make a very small error in the initial velocity of some object that you missile, for example, that you want to put in space for a long time. Then in 1 month your error might be as large as, say, several thousand kilometers. 1 millimeter error in the beginning might map into very high error afterwards. And this kind of behavior is typical for nuclear ядерный распад, как по-английски. Like the amount of radiative material that remains, so radiative decay. When half of the material is destructed every known period of time. So this kind of behavior. And the behavior of the numerical method will come on top of this behavior of the exact solution. So the method itself has its own properties of stability. Okay, let's stop here for today. I'm a little bit tired. So I'll close the video.